Alright, we are in section 5.3. We did a very simple problem. Are you ready for another example problem? Section 5.3. Let's do that. Now, here is the problem. It appears complicated, but it really is a straightforward problem. Think about this. If you think about this, this is an operational amplifier in a negative feedback configuration. Okay, it's in a negative feedback configuration because the output is being fed all the way back into the input. Okay, then it is also an inverting amplifier. Okay, so the question really is, you see, this resistance here is not a constant one, but a variable. Okay, some sigma times 50 kilo ohms. So sigma is a fraction, probably fraction or a multiple. Okay, it can be a whole number, it can be a fraction. Some sigma times 50, that is in series with 12 kilo ohms. So if you think about this, the variable resistance here in series with this 12 kilo ohms, all of that is RF. Okay, all of that is RF. So sigma 50 kilo ohms plus 12 kilo ohms, that's the feedback resistance. So the question is, now this variable resistance, sigma 50 kilo ohms, what is the value of sigma? What is the range for sigma? Sigma max and sigma min, such that the op-amp does not saturate. Okay, so let's do this problem. It's going to become very, very clear, very simple problem once we start doing the steps. Okay, so whenever we don't know what to do, the first thing we do is to write KCL or follow the steps, step 1, step 2, KCL. So if you want to look at the steps, step number 1, okay, step number 1 is the fact that we want to confirm negative feedback configuration. Okay, and like I mentioned, it is indeed in a negative feedback configuration. Therefore, I can assume, for now, assume linear region of operation. Okay, let's assume linear region of operation. Now, in addition to this, that's step 1. What's step 2? Step 2, if you remember, is writing KCL. Okay, write KCL. KCL at Vn. Okay, so Vn, which is this node here. Okay, all of this, that it's a node, right? So there are 3 branch currents. There is one current going to the left, one current going down. There are actually 4. Another current, little in, going in that direction, and of course there is this current flowing here, right? So let's carefully write the expressions here. This is Vn, okay, but remember, when you apply the rule, Vn is going to be the same as Vp, right? Vn is the same as Vp, which is really 0. Okay, so I'm going to make some simplifications right here. 0, In is 0. So we can do that, or we can write it more formally. Let's just leave it as Vn for now. Okay, so Vn minus 250 milli by 1.6 kilo ohms, that's the current through this branch. Vn minus 250 millivolts divided by 1.6 kilo ohms. Okay, now then there is the other branch, which is this right here. Okay, Vn minus 0 volts divided by 6.4 kilo ohms. Okay, Vn minus 0 volts, sorry, divided by 6.4 kilo ohms plus, let's look at the third branch, In equals to 0, I'm going to leave it there, plus, what's the current in this branch? Okay, the current in this branch is Vn minus Vo divided by this resistance. Okay, so let's see. Vn, I'm going to write it here, Vn is on the left side of the branch, minus Vo divided by the total resistance is sigma 50 kilo ohms plus 12 kilo ohms. Okay, I'm going to make room here. Kilo ohms. Why is that the case? Because sigma 50 kilo ohms is in series with 12 kilo ohms. So pretty simple. I have a series combination. Okay, now that's step number 2. Let's look at step number 3, is to apply the different rules. Vp equals to Vn is the first rule, In equals to Ip equals to 0 is the second rule. Okay, in this case, think about it, Vp is tied to ground. Okay, Vp is tied to ground, therefore Vp is 0, which makes Vn also equals to 0. Now you see, here are the rules again, turning out to be your friends. Okay, all of these terms drop off to 0. Okay, 0, 0. So I'm going to rewrite this equation. Negative, so step number 4. Step number 4 is really just rearranging equation. Okay, negative 250 millivolts divided by 1.6 kilo ohms. Now all of this term is going to drop off because 0 minus 0 in the numerator is 0. This term is going to drop off. So I'm only left with V0 over sigma 50K plus 12K. Okay, all of that equals 0. Everybody with me? Now you see, let me rearrange this a little bit more. Negative 250 millivolts by 1.6 kilo ohms is equals V0 by sigma 50K plus 12K. Okay, it's just a matter of manipulation from here. You see, V output, okay, V output is negative 250 millivolts divided by 1.6 kilo ohms, okay, multiplied by sigma 50K plus 12K. Okay, now the question is, we are interested in finding out the sigma maximum and sigma minimum. Okay, so what value can this guy take, okay, for the maximum and minimum values, okay, before saturation? I'm going to say for the op-amp to say in non-saturation or linear region. Okay, so really that is set by the V output maximum V output minimum, right? V output maximum and V output minimum really set those values. Okay, what is the V output maximum? V output maximum is the positive VCC. V output minimum is negative VCC. Okay, V output maximum is plus VCC, which is given to be plus 5 volts. This guy is negative VCC, which is given to be negative 5 volts. It's given in the problem, right? So it's just a matter of equating all of this, okay? All of this negative 250 milli divided by 1.6 kilo times sigma 50K plus 12K is 5 volts. Okay, that's what is the V output maximum. And then you would equate the exact same thing to negative 5 volts as well. Okay, you see what's going on? So the idea is that in order to find the maximum and minimum for sigma, we have to go off of the V output maximum and V output minimum. Because what is saturation after all? Saturation is the point where the V output reaches plus 5 volts and V output falls below negative 5 volts, because there are plus and negative VCC. Okay, so you can find a value. When you rearrange this equation, you see that sigma will come out to be negative 8.8 value. Okay, because sigma cannot be negative. If you have a negative sigma, you'll end up with a negative resistance. So it's not possible to see negative resistance in this course. So we say the sigma minimum is 0. Okay. Similarly, what we do is to equate all of this. Okay. So in this equation, I'm going to copy this, paste it over here. Okay. Now, in order to avoid saturation, we want to make sure that, say, earlier we had this, right? VO is this guy. So VO minimum is negative 5 volts. Okay, negative 5 volts. So rearrange this equation. It's just a matter of finding sigma. Everything else is a numerical value. There is no unknown here. Okay, so you calculate out the value for sigma, you'll get a value of 4. Okay, you'll get a value of 0.4 actually. Okay, you'll get a value of 0.4. Okay, now the result is that this is the VA sigma maximum. As long as the sigma is between 0 and 0.4 value, your op amp will not saturate. Okay, you may not be 100% sure on whether this result makes sense or not. Here is what I invite you to do. Pick a value for sigma that is 1. Okay, if you pick a value for sigma equals to 1 or something above, okay, something above 0.4, you can pick a value of 0.8. Any value that is above 0.4, you will see that if you plug that number into the equation here, sure enough, your op amp will saturate. Okay, your op amp will go below VCC or above positive VCC. It will go below negative VCC or above positive VCC, which means it's saturating. Okay, as long as you pick any value, okay, pick any value, sigma equals to 0.35, sigma equals to 0.1, sigma equals to 0.25. Any value within this range and plug it into this equation, this expression here, you will see that the op amp will not saturate. The output of the op amp will lie in between plus VCC and negative VCC. Okay, so it does not make sense to do the math blindly. What is important is that you have to understand the intuition behind it. Okay, so in order to make sense of the intuition, try to see if these results make sense by picking a value that is above 0.4 for sigma. Then you will see that the op amp will saturate. Similarly, pick a bunch of values, 0.35, 0.1, 0.25 within this range. Okay, when you pick a value within this range, then you will pretty much see that the op amp output will be within plus and minus VCC. So a sanity check is important. Okay, so with that we are going to stop with this section 5.3. We have worked on enough example problems, so that should be a pretty good exercise for you. We will go to next sections and look at more example problems.